Thank you again, Aswin. So since there were a lot of complaints last time about the size of my writing on the board, I thought that I might eliminate some of the problem by using slides. So let me start by reviewing quickly most of the things I said last time, and then let me continue. Okay. So the goal is to explain the geometric Langlands conjecture, especially as it relates to homological mirror symmetry, Hitchin system, and non-abelian Hodge theory. The first of the three will be very brief. It will be mostly this. Much of what I'm saying is just going to be a general review survey, but the new results are joint with Tony Pantev and partially with Carlos Simpson. Okay, so as I was explaining last time, the Langlands program is the non-abelian version or extension of an abelian theory called class field theory or geometric class field theory. And the abelian case is well understood. It's just a theory of a curve and its Jacobian. And I explained last time that there are basically two proofs, a topological one and an algebraic one, of the result in the abelian case. So here they are summarized for you. There was an issue in the naive formulation in terms of the Jacobian, which was that it was not natural. It depended on the choice of a base point. The way to make it natural is to replace the Abel-Jacobi map by, which is a map from C to Pic, or C to its Jacobian, by a map from the Picard across the curve to the Picard, sending a line bundle and a point to the line bundle tensor of the point. So it shifts the degree by 1. And then this map is completely natural. We've just, instead of choosing a base point of the curve, we've included the base point as part of the data. So it says that for every rank 1 local system L on the curve, there should be a unique extension to a rank 1 local system C sub L on the Picard, such that we have this eigenvalue problem. The Abel-Jacobi pullback of CL should be CL pulled back from the first factor tensor L on the other factor. So here's how the extension is supposed to go. The Jacobian is replaced by the moduli stack bun of principal bundles on C, whose structure group is some group. In fact, it's going to be the Langlands dual of the original G. So I'm not explaining what it is. In general, if you have a Lie algebra G, you have two lattices that correspond to it. You have its weights and its roots. The weight lattice is all homomorphisms from the Cartan to C star. The root is a sublattice of that generated by the actual roots of the presentation. And then you can consider any other lattice sandwiched in between the roots and the weights. And a choice of group G such that the Lie algebra of G is the given. Lie algebra is the same as choice of X. So this is a finite difference. This is a sublattice of finite index. So there's a finite number of intermediate lattices, and they correspond to the possible groups. So if G is a reductive group with maximal torus T, then the Langlands dual group is a group, a reductive group that contains its own maximal torus. And roughly the relationship is that the Langlands dual torus is some sort of a dual of the Langlands torus. It's dual in the sense that it's a lattice tensor C star, and you replace the lattice by the dual lattice tensor C star. So a more formal way to say it is that the group of characters of G, that means this lattice corresponding to the choice of the group G, is dual to the, well, it's the co-characters, the dual of the characters of this other group. So this does not show that such a Langlands dual group GL exists or that it is unique, but those turn out to be true. In fact, there is a more elaborate but direct construction where you start from a group G and you can construct its Langlands dual group GL. So just for those who have never seen this, if G is GLN, it is self-dual. If G is SLN, its Langlands dual is PGLN. So in the case of so the Lie algebra in this case is GLN. In this case, the Lie algebra is SLN, which is the traceless matrices. In this case, these two lattices are going to be one will be of index n inside the other. The quotient would be a cyclic group of order n. One of the lattices you can think of as integer n-tuples that add up to an integer. I'm sorry, integer n-tuples that add up to 0. And the other is rational n-tuples with the same property, where the difference between any two of the entries is an integer. So I guess you have to play with that a little bit. But this will be the smallest one, and this will be the largest one. And you can imagine various other things in between. If you do the orthogonal group, let's say orthogonal group of order 2n, it is self-dual. But if you take the simply connected group, which is its double cover, you get a double quotient of this one, which is going to be, I guess we'll call it PO2n. So the diagram, the group of weights divided by roots in this case is going to be Z mod 2 cross Z mod 2. So the diagram looks like this. There's the full group, the zero group, and 3 subgroups of index 2, or of order 2 inside. This one is going to correspond to spin. This will be PO. The one in the middle will be, and I said O, I probably should have called it SO because I want the connected group. I did write it correctly there. And then maybe this is only for n even. So you have these two other versions which give rise to things like E8, which will be self-dual and so on. So Langlands duality at the Lie algebra level, types A, D, and E, the simply laced types, are going to be self-dual in the sense that a group corresponding to one of these goes to another group for the same Lie algebra. And always the simply connected group goes to the adjoint group and various things in between. And then B goes to C And I guess for F and G, something slightly funny happens. They each go to themselves, but in a non-trivial way. I might say a little more about what's funny about F and G later on. Okay. So that's the Langlands dual group. Let's focus on the case of GLN, in which case the thing is self-dual, or in SLN where it's almost self-dual, which just goes to PGLN. Okay. So the analog of the Abel-Jacobi map are the Heckle correspondences, H. So I explained last time that a correspondence is just a subvariety of the product. And in this case, the subvariety parameterizes triples, V, V prime, and X, where V and V prime are isomorphic as well away from X. If you want to be a little more careful, you should include the isomorphism beta as part of the data. So you can talk about quadruples, V, V prime, X beta, where beta is a choice of isomorphism away from the point. And if you want to get a finite dimensional object, you need to specify the order of growth of beta, which we will do in a minute. So let's just illustrate this in the case, in the abelian case, the one that I was dealing with last time. These become triples, a line bundle, another line bundle, and a point, where the line bundle L prime is obtained from L by tensoring with some fixed power of the line bundle OCX. So if you fix L and you vary the point X, that just gives you the Abel-Jacobi map. So that's the sense in which this Heckle correspondence generalizes Abel-Jacobi. But if you go to non-abelian cases, then it's really a correspondence, not a map, in the sense that for every V, there would be a positive dimensional family of V primes, and for every V prime, there would be a positive dimensional family of V's. So it's many to many. In fact, in the case that Tony will study next week, where the group is SL2, the fiber is always going to be a P1. Well, generically P1. It's a P1 because given a rank 2 vector bundle and a point, the set of possible modifications at that point is parameterized by the projective line parameterizing all one-dimensional subspaces in the two-dimensional fiber of the vector bundle at the point. So you get that the fiber is P1. And that's correct at the stacky level. If you try to do it at the geometric level of moduli spaces, you find that sometimes you start with a stable bundle and you modify it and you get an unstable bundle. So that's not a legitimate point and you have to start resolving things. So if you're trying to understand it geometrically, you get more complicated situations where the Heckle fibers are rational curves, but they may be reducible. They may not be a single conic, but a bunch of lines in some pattern. And we'll have to describe that explicitly in some geometric situations. But if you stick with the stack, then it's always just tautologically a projective space, or more generally a Grossmanian. Okay. So for bigger groups, this is what I promised about the betas. For bigger groups, there are many ways to specify allowed order of growth of beta, and they turn out to be indexed exactly by dominant characters. So char is that lattice that I had over there, the X, over there. And for each mu, which is a dominant character of the Langlands dual group, or dominant co-character of G, there will be a way of measuring the order of growth with respect to a one-parameter subgroup going in that direction. So that means that there's a collection of Heckle correspondences, not just a single one, but a whole family of H mu's indexed by mu's in some cone, lattice points of some cone. And each of it induces a Heckle operator on various categories of objects on Bun. So let me just make sure we see what happens in the abelian case. In that case, the characters are the integers. The dominant cone is just the non-negative integers. There's a generator 1. So there's a basic Heckle correspondence, which is the Abel-Jacobi map. It sends a line bundle to a line bundle tensor O of X. And all the others just send it to L tensor L of L tensor O of nx for some non-negative integer n. So in the abelian case, you don't really need to worry about the rest of the cone. It just has one generator, and you're just looking for eigen objects for that generator, for that Heckle operator. But in general, for more complicated groups, we have a whole infinite collection of H mu's, and it's not clear why, in what sense we expect to get eigensheaves for all of them. So the point is that all of these Heckle operators form a commutative algebra. In other words, the operation of starting with a vector bundle and a point, and modifying the bundle along a 7-dimensional subspace of the fiber at that point gives me some Grassmannian. Now, for each point of that Grassmannian, I can modify by a 12-dimensional subspace and get some other Grassmannian fibered over this Grassmannian. So the composition of these two Heckles means I'm replacing the point by this Grassmann bundle over Grassmannian. Commutativity says that I can also do it the other way. First take that Grassmannian of 12-dimensional subspaces, and then a fiber over that, the 7-dimensional spaces. And the claim is that these two operations commute, which is very hard to track and justify until you realize that the family of all these operators, so they depend on the cutoff mu, but they also depend on a point P of the curve. Okay? And we want to show that two of these operations, let's say H mu of P and H nu of Q, commute with each other. As long as P and Q are distinct, this is completely obvious. You're doing some modification at P and some other operation at Q, or you do them in the reverse order, it doesn't matter. Now take the limit as P approaches Q. Just by continuity, you see that they commute even when P equals Q, which wasn't at all obvious working just at P. So the reason you're getting a commutative algebra is because you're allowed to separate the points, work there, and then bring them back together. Okay. So we have a commuting algebra, and therefore we may as well we're allowed to talk about simultaneous eigenobjects for the entire algebra, and those would be the objects that the geometric Langlands correspondence predicts. And I already told you what a correspondence is, so I'll skip that. So geometric Langlands conjecture says that an irreducible geolocal system on C determines a perverse sheaf on Bann. Perverse sheaf, we will just think of it as a local system on the Zariski open subset, which is a simultaneous eigensheaf for the action of these Heckle operators. And this turns out to be the right generalization of the naturality with respect to Abel-Jacobi. And a perverse sheaf is the unique middle perversity extension of a local system from a Zariski open subset. There are fancier versions of the conjecture which try to recast this as an equivalence of derived categories of D modules. So two derived categories. One is D modules on Bann, and the other is coherent sheaves on Locke. So roughly speaking, we have Locke and Bann. And Locke is roughly twice the size of Bann. In fact, we'll talk about that in more detail in a minute. So on Locke, you look at O bundles, while on Bann, you look at O modules. Well, here you look at D modules. And again, the thinking is D is roughly twice the size of O. So either way, we've there's one doubling, but the doubling happens in different places. So you look at these two derived categories, and you want some sort of equivalence between the derived category of coherent sheaves on the module of local systems versus D modules on Bann. And one of these should be for the group G, and the other should be for the Langlands dual group. the convention that we followed is the local system has group G, so the bundles have a Langlands tacked on there somewhere. So that's bundles with structure group is the Langlands dual group. And there are many related conjectures and extensions. Some of them go along the lines of the things we heard this morning from Mochizuki about going to punctured curves via parabolic bundles and local systems. And some of those inevitably will come in below. So let's finally try to state a version of the conjecture. It says that an irreducible geolocal system, let's call it V, on a Riemann surface C, gives a unique object on the other side, which is an automorphic D-module C sub V on the moduli space Bun. So this is what I'm calling there Bun L. It's Bun for the Langlands dual group of Langlands dual LG bundles on C. And automorphic means that it's a simultaneous eigenobject of all the Heckle operators. Which is a Langlands dual group, okay?
Is there a meaning for irreducible on the D modules?
You mean in the cases?
Or in other words, if I wanted to relax and consider reducible local systems, I would get different.
Yeah, so I talked about that a little bit last time.
Oh, that's the
when you have an irreducible point that, when you have a reducible local system, that's an example of a singular point of the moduli space, and that's where you have to impose the Arinkin-Geitzgori conditions on the singular support in order to not overcount things.
What changes on the D module?
Okay. Hold on one slide. I'll say a little bit about that in a minute. So this is what I was trying to write there. So the fancier version, to the extent that it is true, says that we have categorical equivalence like this, which is uniquely characterized by the property that it sends structure sheaves of points on this side, right? So the basic conjecture says you start with a local system, or an irreducible local system. The fancier version says start with any coherent sheaf on loc. You think of the local system itself as its own structure sheaf, which is S sheaf on all of loc, but it's supported just at the one point. So it's characterized by the property that when you restrict to the ones that come from there, the thing that you get on the other side should be a Heckle eigen D module, okay, in a sense. There are, again, more general ways of saying it, which I guess physicists would say that it takes Heckle operators to line operators or something like that. So tensorization on one side gets converted to a Heckle operator on the other. All right, so and again, use the cutoff. So the first problem with this is that it's wrong, and Arinkin and Geitzgori have done a lot of work on formulating the right version of this in the case where you're allowing singular points. Those corrections are not going to be relevant to anything I say, because what we're focusing on is construction of automorphic sheaves. We start with some data on the local system side. In fact, we'll always be starting just with a particular local system and trying to create a local system on some Zariski open subset of Bun. So we'll just start with a local system that's good enough, and then presumably in further iterations, you'll study what happens when your input becomes singular and how the construction gets modified. Yeah, even in the case of vector bundles, Yeah, so I mean, the terminology of an irreducible versus reducible local system is geared towards the case of vector bundles, towards GLN. In other cases, you talk about local systems where structure group could be reduced to some Levy subgroup, it's actually reducible. You can actually talk about reducible and irreducible just in the case of vector bundles. So that's what I'm focusing on. So a lot of work has been done on this for 20 or 30 years now, and here are some of the people who've made great contributions. I think the basic version is known for GLN, and Geitzgoi feels that he's close to proving the fancier version for GLN as well. Not much is known for other groups, as far as I'm aware. There's some work of Heinloth, among others, on the parabolic case. So one thing that we're trying to do is to give a different construction where we're producing something that's more explicit, where we can really analyze the object we get, but we're relying on a heavy machine developed for us by Mochizuki and collaborators. So instead of reducing it to a lot of very abstract algebra, we're reducing it to solving some hard differential equations, which we're assured can be solved. So before going into this, I think I still have some time. Let me make a quick detour about the relation of the story to homological mirror symmetry. I'm not going to pursue that beyond the next 2 minutes. So the idea is that the curve C and the group G determines the moduli stack Higgs of all G Higgs bundles on C. So I assume everybody knows by now what a Higgs bundle is, so I don't have to repeat that. The moduli space itself is symplectic. In fact, it has a hyperkähler structure. Depending on which version you use, it either is the same as the cotangent bundle of Bunn, or it contains it as a zero-open subset. The distinction is whether you're looking at the moduli space or the moduli stack. The moduli stack is just a cotangent bundle. So a Higgs field, or a Higgs bundle is a vector bundle, a G bundle together with a Higgs field, which is just a cotangent direction to the base. So at the stacky level, they're equal. If you impose stability, the stability conditions turn out to be a little different. So Higgs contains the cotangent bundle, but it's actually bigger. It's a partial conjunctification. At any rate, the fact that it's hyperkähler gives you a hyperkähler rotation or a spinor structure on it. The hyperkähler rotation gives the moduli stack lock of geolocal systems on C. So another way of saying it is that there's a one parameter family of complex structures on this thing. At one value, you get this Higgs moduli space. At most of the other values, you get the lambda connections that we saw this morning. So the moduli spaces are lambda connections. So in the, yeah.
This hyperkähler rotation works also for stacks.
Yes. You can formulate it for the stack. So Hitchin's integrable system is a particular integrable system. It's a Lagrangian fibration on the Higgs moduli space over some base B, which I will describe for you soon. But let's just accept that it exists. And we'll see the details in a moment. The point is then that this symplectic or hyperkähler space Higgs has not but one but two different Lagrangian fibrations. So one is the Hitchin map, and the other is just the projection from the cotangent bundle of Bun to Bun. So that's just a rational map if you're looking at the geometric versions where it's actually a little bigger. So you see that the complications are going to come from the locus where pi is not defined. And that comes from bundles that are stable as a Higgs pair, but the underlying naked bundle is not stable. So those are going to play a key role in much of what follows. Anyway, the homological mirror symmetry interpretation is that the desired Hecke eigensheaf on Bun can be obtained explicitly by applying family flare homology to Hitchin system. So let me say it and then I'll write it on the board. So, I'm sorry. The automorphic sheaf that we're looking for, CL, should be realized as the relative flare homology between two Lagrangians in Higgs. One of them is going to be fixed, the other is moving. It's parameterized by a point of Bun, so therefore it produces for you an object on Bun, and that object will be a D-module, or generically it will be a local system. And I'm calling it Bun, but it's Bun for the, with my convention, I should have called it Bun L. It's Bun for the Langlands dual group. So view your input L as a point of Higgs. A priori, it's a point of lock. You do a hyperkähler rotation, you identify lock as Higgs. So think of it as a Higgs bundle. Its Fourier-Mukai dual is going to be not a point, but a Lagrangian subspace, and not in Higgs G, but in Higgs GL. So these two spaces are going to be sort of dual to each other. Again, I'll explain that in more detail in a few minutes. And this duality, for physicists, this will be a T-duality, will convert a point here to a Lagrangian there, and vice versa. So the input L gives me an object which is one Lagrangian in Higgs. So this is the fixed object. L is the local system. That's the input for the basic version of the conjecture. Yeah. So L is just a local system. I might have called it V. It's yeah, sorry about that. So L is the same as V. So this is the fixed object. The moving object is going to be just a general cotangent fiber of Higgs. In other words, I'm taking my L gives me one Lagrangian in Higgs. And I'm going to pair it off against a moving family of Lagrangians, which are the fibers of this map. Let me try to do that again on the board. Here's Higgs. It has two Lagrangian fibrations. One goes to Bun, and the other goes to the Hitchin base B. The fibers this way are just vector spaces. The fibers that way are going to be abelian varieties. So I'll try to draw them as something more complicated. Okay? I'm trying to produce an object on Bun. That object should be, well, a local system over the good locus, and then it'll get corrected somehow to a perverse sheaf. So given a point here, a general point, I want to get a vector space that I associate to it. So what I do is I take the fiber over that point, and then I compare it with this. Roughly speaking, I take their intersection and take the free vector spaces built on that finite set of points. And then you can see where the thing is going to jump, where the two Lagrangians are not transversal to each other, which again is closely related to to the difference between Higgs and cotangent bundle of Bunn. So this is the basic picture. Family flow homology basically makes sense of taking the vector space on the intersection and moving it into a local system. So this is the homological mirror symmetry interpretation of the basic conjecture that says that starting with a local system, which I think of as a point of Higgs, I plug it in here, I get an object on Bunn. Question? This Bunn, yeah, it's absolutely correct. It should be L Bunn. Pardon? And L Higgs and LB, which actually is canonically identified with B. Say that again. I just can't hear you.
The family flow homology would be defined over the logic of the.
Yes. The geometric object that we're trying to construct, the proposal is that on the Zariski open subset of Bunn, namely specifically the locus where the two fibrations are transversal to each other, it should be just the free abelian group spanned by the intersection. That is a simple, concrete local system that you get. And yeah. That is, yeah. So the full version of the conjecture is supposed to follow from the full version of homological mirror symmetry, which, let me just outline it like this. So it's something like this. The Fukaya category of Higgs for the Langlands dual group should map to the derived category of D modules, basically by this construction. The same Fukaya category maps to the other thing, coherent sheaves on look, by a version of the SYZ duality or T duality for the physicists again. So the point is that these spaces are going to be, you're going to have these two Lagrangian fibrations, the Hitchin fibrations for G and for GL. There will be an identification of the base in such a way that the fibers are exactly dual to each other. So one equivalence is supposed to be the SYZ identification, and the other equivalence is supposed to be this family flow homology. So this is an identification proposed by or based on ideas of Muhammad Abu Zaid. So this would be the interpretation of the full conjecture, while the basic version that produces the automorphic object is described here. Okay, so let me not dwell on this approach. I have half an hour. Let me try to focus on the part that I can really do. So I'm trying to say it in a little more detail here. So L, the local system, is a point of log, so I transform it to a point of Higgs by the hyperkähler rotation. Fourier Mukai is a Lagrangian in Higgs, that's one, and then there's the other family of Lagrangians coming from the cotangent fibers, and I take their intersection. Okay, so the work that I describe here is based on abelianization using this Hitchin system. So we know what a Higgs bundle is. It's a bundle together with a one-form valued endomorphism of the bundle in the case of GLN. And in general, you'll take, instead of an endomorphism of the bundle, you'll take a section of an associated bundle associated through the adjoint representation. More generally, for a general group G, you just replace the endomorphisms of V by the adjoint representation of V. So Hitchin studied the moduli space of such Higgs bundles subject to stability conditions and showed that it is an algebraically integrable system. It's algebraically symplectic. It admits a natural map H from Higgs to the base to vector space B, such that the fibers are Lagrangian subvarieties. So B parameterizes speckle covers, which again we've seen already in several of the talks today. And in fact, the fiber is an abelian variety. In the case of GLN, it's just going to be the Jacobian of the speckle cover. In other cases, it's some other abelian variety related to it, so it's called a prim variety. Okay. So the description in terms of speckle covers is a little ad hoc in that it depends on choosing a representation of the group, and there's a more uniform description in terms of generalized prim varieties. So what is the Hitchin base? In the case of GLN, it is H naught of K plus H naught of K squared plus H naught of K to the N, where K is the canonical bundle of your curve. For SLN, you skip the first term, you start from K squared, and you go to K to the N. And for a general G, it's going to be the direct sum, I going from 1 to the rank of the group of global sections on the curve of K to the power DI, where DI are the degrees of the invariant polynomials. So that's a natural generalization of these two things. And what's the map? The Hitchin map from Higgs to B takes a pair V and phi and sends it to the characteristic polynomial of phi. So phi is an endomorphism taking values in some funny line bundle. It doesn't take values in numbers, but in one forms. So its trace makes sense as a global one form. And the next coefficient makes sense as a global, it's not a two form, it's a quadratic differential, because it's a symmetric power, and so on. So the ith coefficient is a section of K to the I in the case of GLN. And the part that you can make sense of for a general group is what I wrote here. So an alternate description is that you take the Cartan subalgebra for your group. So in the case of GLN, that's just all n by n diagonal matrices. For SLN, it's traceless diagonal matrices, and so on. You tensor it with K. Let me tensor it on the other side with K. So that's a vector bundle on the curve of rank R. The Weil group acts on it. The Weil group, in the case of either GLN or SLN, is the symmetric group on n letters. In general, it's sort of the natural finite symmetry group of the picture. So you can divide by the action. Well, W acts on T, and it doesn't act on K. So you can write it this way, or you can put the parentheses this way. Think of it as some sort of a weighted tensor product of this with that. So a little theorem of Chevalley says that T mod W is always going to be a vector space. It's a geometric quotient by a complicated action, so it's not at all obvious, but it's true. So in the case of GLN, it just says that, it's just this elementary theorem, fundamental theorem of symmetric functions that says that any symmetric polynomial is a polynomial in the n, elementary symmetric polynomial. So the ring of symmetric polynomials is a polynomial ring. So it's a functions on some vector space. So this is a vector bundle over the curve. In fact, it's a sum of line bundles corresponding to the pieces, and the degrees of and each of these line bundles is just going to be a power of the canonical bundle, and the power would be the degree of the elementary polynomials. So the alternate description is take this vector bundles, take global sections of that. That's the Hitchin base. So a point in the Hitchin base let's put it this way. If you take the Hitchin base across the curve, there's a natural cover where you look at global sections of KC tensor T without the W. So this is a Galois cover where the Galois group is W. Given a section here, you look at all the ways of lifting it. Maybe I didn't say that quite right. But so a point B in the base determines a copy of the curve C, and its inverse image so if you take one horizontal copy of the curve C, take its inverse image, that will be the cameral cover. The idea is, in the case of SL3, the spectral cover is going to be an n-sheeted cover or a 3-sheeted cover. This thing will be a cover of degree n factorial, or 6. And above each point, you have a picture of the Cartan and the chambers, and it's all rotating around as you move around the curve C, and you're choosing one chamber above each point. So that's where camera comes from. So the most natural description of the Hitchin system is in terms of this description of the base, and the use of this family of cameral covers and Weil action on them. So where were we? So that's the uniform description in terms of generalized primes of cameral covers. You can say more or less exactly what the fiber is. So H inverse of a point B is going to be roughly, you take homomorphisms from lambda, which is the character lattice of your group, to the Picard of C tilde, the while group acts on lambda because it's, well, just the while group is the symmetry group of the lattice. It also acts on C tilde, therefore it acts by pullback on pick of C tilde. So you can look at those homomorphisms that are W equivariant. And this is what's called the prim. It's lambda itself, just all copies of the integers. Homomorphisms from lambda to the Picard gives you all copies of the Picard. So that's a little discrete part plus a big abelian variety. And this is going to give you some abelian subvariety of the product. And that's going to be the generalized prim. In the case of GLN, it is just the Jacobian. In other cases, it's the right thing. I said that it's only roughly equivalent because it's actually not quite this, but there's some Jobiness and some. It's true on the continuous part. On the discrete part, it's a little hard to describe, and it's worked to death in a paper I wrote with Guides Goris some 10 years ago. Okay. So I'm going to finish today by talking about the result that I have with Tony about the duality of the Hitchin system. So roughly speaking, it says that there's a canonical isomorphism between the bases B and BL of the Hitchin system for the group G and its Langlands dual group GL. It takes the discriminant in one to the discriminant of the other. The discriminant is the locus of spectral or camel covers that are singular. The generic one is going to be non-singular, but when branch points come together, you do get singularities. Taking the discriminant in one to the other. Away from the discriminant, I have honest smooth spiral covers, so I have honest Jacobians and Picards and prims, and these are going to be abelian varieties. So what we do is we exhibit a canonical duality between those fibers.
The statement that the discriminant goes to the other, is it harder to prove than saying that the Hitchin base is sort of the same for G and GL?
Well, as Clinton said, it's a question of what is, right? The Hitchin bases for the two groups are not the same. And what we're saying is that there's a canonical identification between them. Now, each of them carries a discriminant, and I'm saying the natural identification that we give takes the discriminant in one to the discriminant of the other. It's not a tautology, but it's true. The case of the groups of type AN, so GLN, SLN, and PGLN, had appeared earlier in work of Hausel and Thaddeus in the context of hyperkähler mirror symmetry. So in a sense, we're generalizing that to other groups. I mentioned before that there's something funny happening for some groups like F and G. What happens is so G2 is this Lincoln diagram, and F4 is, did I get it right? I think that's the right description. So what happens in these cases is they are Langlands self-dual. So therefore, there are two ways of identifying B with BL. One is the identification that we give. And the other is just the fact that the thing is self-dual, so it's actually the Hitchin base for the same group. And these two identifications are not the same. So that's the delicate thing that's happening. What's happening is that our identification in these non-simply connected, in these non-simply laced cases, is going to send short roots to long roots and vice versa in each of these cases. Well, of course, the other identification sends each point to itself, so a short root goes to a short root, and a long root goes to a long root. So the natural identification that makes this work, in the case that there's already a God-given identification of the base, is not that God-given identification. different thing. And that's why it's not at all obvious that this thing is going to take the discriminant to the discriminant. They work with moduli spaces. Yes, we're working with a moduli stack. Yeah, I'm not sure how much what it would be involved in either converting the result to stacks or converting our result to spaces, but yeah. Yeah, the current versions are written in different languages. Yeah, modulo, assuming that it doesn't matter which one you're talking about, ours is a generalization. But you're right, it's a generalization of a slightly different result. So there are. So the key application that we have for this result is that the Heckle correspondence admits an abelianized version, where abelianization means lifting from Bunn to Higgs. And our results allow the construction of eigensheaves for these abelianized Heckle correspondences. And that's going to be the basis for our program in general, as I'll explain next time. So as I've already mentioned, on Higgs there are these two different Lagrangian fibration. By now we really understand them, right? There's the Hitchin fibration and the rational projection. The Heckle correspondence is a sub-variety or sub-stack of Bunn cross C, defined by something that says that one bundle is a modification of the other at the specified point. The abelianized Heckle correspondence, H tilde, is going to be the analogous thing where we replace a bundle by a Higgs bundle. It's not going to be just the pullback from Bunn to Higgs. It's going to be much, much smaller than the pullback. So this may not be in my notes, so let me write it. I'm thinking of this in the context of stacks mostly. So, yes, so I'm sorry, I am in the context of stacks, and therefore I don't need to worry about the fact that it would be rational if I were doing it in geometry. Thank you, yeah. So, in Heckle, I was looking at V and V prime in a point P, such that V prime is some modification, something like this. I'm only doing the GLN case. You can do a slightly fancier version for any group. Heckle tilde starts with a V and a phi, and a V prime and a phi prime, and a point P. And the condition is that, well, V is contained in V prime, contained in VP, and phi prime. So let's see, so we can go from V to V prime by this inclusion, from V to V tensor something by phi, from V prime to V prime tensor the same something using phi prime. And then the inclusion is again giving me a map this way. And I want this to be commutative. So given phi prime will be unique if it exists. So that's a big difference between the lift of H and the H tilde. The lift of H would just be all pairs V and V prime satisfying this property. Inside that, I'm taking a much smaller correspondence where I'm also imposing a compatibility on the phi. I'm saying that given a phi here, so the modification from V to V prime should be along a subspace of V, which happens to be invariant under phi. So in the generic case where phi is a diagonal, a semi-simple diagonal matrix with distinct eigenvalues, then V decomposes into a sum of n distinct lines, and I'm only allowing modifications based on a subspace that's a combination of some finite subset of those lines. So given a V and a phi, there will be only finitely many V primes that I can get. So instead of having to get this infinite dimensional in scheme and then having to truncate it to get finite dimensional pieces, I'm just getting a finite collection altogether. So it's like a graph theoretic simplification of the big object. So these are the Abelianized Heckle correspondences, and they are going to define Abelianized Heckle operators. And the result is that these Abelianized Heckle eigensheaves that I promised, which is going to be direct images of degree 0 line bundles on Hitchin fibers. So the trick is that we're thinking of Bun itself as a base. And it has a spectral or cameral cover, and that is the Hitchin fiber. So where previously we're thinking of the curve C as the base and the spectral cover as some finite shaded cover of that, instead we're thinking of the moduli space of bundles as the new base, and it has a spectral cover, which is an abelian variety, the fiber of Hitchin. So in order to do that, we need to know non-abelian Hodge theory, not just on the curve, but also on higher dimensional varieties. And I believe we're going to hear from Michizuki about that tomorrow. Fortunately, that'll be before my next talk when I really need it. So the timing is working out very nicely. So it's very tempting to try to understand the relationship between this Abelianized result, which is relatively easy, and the deep, mysterious full geometric Langlands conjecture. So the Bailyn-Sundrinfeld version of that is they interpret the full version as a quantum deformation of a classical theory, which is essentially this Abelianized version. So their emphasis is on quantizing Hitchin system, which leads to investigation of opers and so on. And then Arinkin has done some work in that direction. Basically, he does the first order deformation, the first step in writing down a quantum deformation of the classical version. But it just looks incredibly difficult to extend it step by step to higher orders. And our entire point, in a way, is to say, maybe you don't have to do it step by step and to actually write down all steps of some formal expansion, which will give you the quantum deformation. Instead, do it geometrically. The hyperkähler rotation is going to give you the global object, and you're just expanding that to arbitrary orders at your given point. So, but in order to do that, you need to have the analog of this hyperkähler rotation in the higher dimensional case. So this is what I'm going to explore next time, the possibility that the Abelianized version of geometric Langlands is in fact not just a quantization, but it's actually equivalent to the Abelianized version, where instead of doing quantum deformations, we do the hyperkähler rotation and then truncate that to different orders. So this is where the lambda connections come in. The lambda connection is the natural, the lambda in the lambda connection is the natural parameter on the twistor space. It's fibered over the complex Z line or the lambda line, the Linz lambda line, and it has a Z equals 1 interpretation, which is the full solution of GLC. So instead of starting at 0 and expanding order by order hoping to get some convergent expression that you can then evaluate at 1, you just use a global argument over the entire twistor space to get something over the whole thing, and then just specialize directly at 1. And this leads to non-abelian Hodge theory. I have, well, let me just start a quick review of that. Fortunately, I don't really have to do that because we've heard most of what we need from Mochizuki's talks. So non-abelian Hodge theory, as developed by Hitchin, Donaldson, Collette, Simpson, Saito, Sabah, and especially Mochizuki, establishes under appropriate assumptions the equivalence of local systems and Higgs bundles. It's done by introducing a richer object, the harmonic bundle or the twistor structure, depending on the author that you follow. So this structure is introduced, and it specializes to both the local systems and the Higgs bundles. So those are the Collette part and the Simpson part of the story. And it's closely related to Deline's lambda connections. Again, we've already heard that. The projective or compact Kähler case, as well as the one-dimensional open case, were settled by Simpson 20 years ago, although I guess there was a gap in the one-dimensional case, which Picard and Bolch filled in. At any rate, by now this is completely understood. But the open case in higher dimensions had to wait fairly recent results by Saito, Sabah, Yostian, Tsuro, and especially Mochizuki, where so the higher dimension theory produced an equivalence of parabolic local systems and parabolic Higgs bundles. This is quite analogous to what is obtained in the compact case, except that the objects involved are required to satisfy 3 key conditions discovered by Mochizuki, which I'm going to review for you early next time. And then I want to outline how we're proposing to use those to construct automorphic sheaves as predicted by geometric Langlands. And since this is a physics/math conference, I should mention that at least some of the inspiration for this comes from the work of Witten with Kapustin and with his other collaborators, where this hyperkähler rotation occurs in a slightly different context, but can be related to this. So I'll do this next time. So thank you.
Questions?
So when you're working in the stack context, does the shaky locus play a role in?
Absolutely.
It does.
Yes. So, well, I haven't quite defined shaky, but the key locus is going to be the wobbly locus. The wobbly locus is, so I'll give the definition. There's a standard notion that goes back to that paper I mentioned last time by Lomond from 1987 of very stable. You say that if a bundle is very stable if every nilpotent, the only nilpotent Higgs field on it is the zero Higgs field. So it says that the 2 fibrations, the Hitchin fibration and the cotangent fibration, intersect at a unique point. Of course, to multiple. Yeah, I'm ahead of them. Of course, they'll have to intersect to a high degree, but you want the intersection to be supported just at that one point. One result that Lomond proves is that this is a non-empty open condition. So most bundles are very, very stable. And the other thing that he proves is that very stable implies stable. So the question is, what can you say about bundles that are stable but not very stable? So we call those wobbly. They're stable but not very stable. So those come in as the key objects that we need to focus on, basically because even when we start with a non-parabolic situation, we start with a compact curve with no marked points on it, the objects that you get on the other side are going to be parabolic. And the divisor in which they're going to have parabolic structure is going to be this wobbly locus. The shaky bundles, as you know well, are closely related to the wobbly locus, so they come in indirectly through that. But somehow, even in the Stacky case, the Heckle correspondences remember the difference between the different notions of stability for vector bundles and Higgs bundles. So I'll try to emphasize that next time.
So you mentioned that the conjecture needs to be corrected early on. So that preceded Berlinson and Drinfeld, or it was after that? You mentioned
This is fairly recent. It's from the last 2 or 3 years. It's work of Arinkin and Geitzgori.
Right. So how does it sort of modify what Berlinson and Drinfeld sort of stated in their claim? I mean,
How did it modify Berlinson and Drinfeld?
yeah, that's right.
Well, they developed a spectacular general theory, but their objects they can't prove geometric Langlands in general. They prove it for opers. Inside all of loc, which is, we want to say that for every local system we get something, an automorphic sheaf. And the set of opers is a Lagrangian subvariety inside the local system, so it has half the dimension. So for opers, they can do something and produce a D module on the other side. If you restrict just to those, you don't see the problem. Those are very simple differential equations where somehow you're putting a condition of non-degeneracy, which tells you that those are going to be non-singular points. My understanding is that you don't have to apply any modifications to those. The modification lives in the bulk of the modular of local systems away from the opera locus.
So is this obvious from the gauge theoretic approach? Like, can you glean from the gauge theoretic approach that this, what Geitzgori and Arinkin are doing, can you see it from the gauge, the Kapustin and the Witten thing? Is there any way to see how this can happen physically?
How what happens?
The modification that you just mentioned?
Yeah, so I was asked that at the end of last talk, and I said a little bit about that. I think that was before you arrived.
Yeah.
The issue is, so you start with a local system. You think of that as a sheaf on the modular space of local systems, which is just the structure sheaf of a point. And then to that you want to assign something. That is perfectly good operation when your point is a smooth point of the modular local systems. But what happens when it's a complicated point? It can be complicated in 2 ways. It can be singular, or it can be a stacky point. It can have sort of higher order. It can be singular, or it can have the full structure that you want to consider is the structure from derived algebraic geometry. So you can have sort of positive cohomology or negative cohomology. Either one can cause trouble. So when you have points with a rich structure, there will be a very rich collection of sheaves that you can take that are supported set theoretically at that point. It turns out if you look at all of them, that's too big to have an analog on the other side. So what Arinkin and Geitzgori say is you have to find a way of restricting to just the right collection in that case. And for that, they define a notion of a singular support of a sheaf, and they want the singular support to be Lagrangian. And that's their condition. So that's their reformulation of the generalized conjecture.
Witten has a conjecture for how to try to get this.
One pass.
It involves
Well, okay, in the Kapustin-Witten picture, you're supposed to start with some boundary conditions in 4 dimensions. So Witten and Gayoto-Witten have these works on studying boundary conditions in more detail. So there are these 2 sides, automorphic and Galois. So conjecturally, this is what they say: if you include a NAM-pole boundary condition on the Galois side in the reduction, it sort of looks like some of the modifications that. Yeah, but I don't know a way to make this precise.
Okay, thanks.
Actually, I had a question. Could you just repeat why you had to consider the spectral curve over Bun-G, and why non-abelian Hodge theory over Bun-G becomes relevant?
Yeah. I think the simple answer is no. And the next level of answer is that that's essentially what I'm going to be spending the next hour talking about. So I'm going to give a detailed outline of how we're trying to do this. We're going to start with the local system of the curve. We're going to convert that to a point of Higgs, thought of as a sheaf on Higgs. We're going to do the easy part of the duality, the Abelianized version, to get a line bundle on a Lagrangian inside the Langlands dual Higgs. And then the support of that is the Hitchin fiber. So that is a finite cover of Bun. And we want to now focus on that situation. We interpret that Hitchin fiber as not just a cover, but a spectral cover of Bun, and use non-abelian Hodge theory to convert that back into the right kind of object, which is a local system or a D-module on Bun. Because what we get, we're doing the work purely in the holomorphic category. We're going from eigensheaves on Bun to eigensheaves on Bun once we've added the Higgs stuff. We use the forward direction of non-abelian Hodge theory at the curve level, but to go back from the holomorphic stuff to the local systems, we need to do non-abelian Hodge theory on Bun itself. And the spectral cover is going to be the Hitchin fiber.
I should have worded my question differently. So what does it mean to say it's a spectral cover of Bun-G? That's all I was asking. Like for the usual Hitchin base, I think of the characteristic polynomial and so on. But what does it mean to say it's a spectral cover of Bun-G?
Okay, so again, I think this is going to be explained tomorrow morning. Okay. But a Higgs bundle in higher dimension is a vector bundle together with an endomorphism valued in 1 forms, not in the canonical bundle, but in 1 forms. Of course, and there's a local condition that says that the different pieces of that, if you write in components, commute with each other. So there's a notion of a Higgs bundle, and corresponding to it, you have a spectral cover, as before, and that's the notion that we get.